Hello, hello. After some practice with finding electric force, when you are given two charges and the distance between them, we're going to look at when we have more than just a couple of charges and when we need to find what is called net force. You remember how to find net force. It's the addition, vector addition, so if the forces are opposite each other, we will be subtracting them, and if they are in the same direction, we will be adding them. So in this particular case, we are interested in the net force on the charge in the middle. Let's see. First off, let's figure out what kind of forces are applied to that charge in the middle. It is negative, and the charge on the right is positive, so it's going to be attracted to it. The charge on the left is also positive, and what you know, it has the same magnitude as the charge on the right. Well then, what is there to calculate? Nothing. In this case, we have what is called an equilibrium. Net force, net electric force for that matter, equals 0, because the two charges are attracting it equally, and therefore it has 0 net force. Had we changed one of the charges to, say, 15, or maybe moved the 3 microcoulombs to the left or to the right, we would end up with a different thing. Oh, and by the way, look at that. I see a little boo-boo here. Let's say I want to find the net force on the 5 microcoulombs. That is on the left, for example. Let's see. It will be attracted, absolutely, to the negative 3 microcoulombs. So here we go. It is being attracted to the negative charge, and it is being repelled by its counterpart, which is 5 microcoulombs. 5 microcoulombs is greater than negative 3, right? So the force should be greater. However, remember the formula for electric force, Q1, Q2, absolute value, R squared. This is more important. The distance is twice as big between the 5 microcoulomb charges. So that gives me an idea that probably the repelling force is going to be smaller, even though 5 is greater than 3. But the distance is double. So I'm just going to draw it like that. Now, to find net force on our 5 microcoulombs, we're going to say 899 times 10 to the 9th, which is kc, multiplied by, each time it is 5 microcoulombs, so it's going to be 5 times 10 to the negative 6th. And then the force to the right is caused by this charge, which is, with absolute value, I'm just going to use 3, 10 to the negative 6th. And the distance between those two charges is 0.5. So when I square the 0.5 meters, it's going to be 0.25. That's the force to the right. The force to the left, since it's to the left, I'm going to subtract it. It's going to be 5 again times 10 to the negative 6th. And the distance between those two is 1. All of that would give me my net force on the charge of 5 microcoulombs, which in my case is on the left. Grab your calculators and figure out what the value will be. Before we do that though, let's make our life a little bit easier. So I have 9th and negative 6th. That would give me 10 to the 3rd. And then these guys have 10 to the negative 6th and 10 to the negative 6th. So what I can do is 8.99 times 5, and then times 10 to the negative 3rd. We'll take out these. And then what I have left is just 3 over 0.25, so that's 12, right? And then we have 12 minus 5, that's a 7. So think about this. 5 times 7, that's a 35. 315 times 10 to the negative 3rd, which is 0.315 newtons. And the force is to the right because the force to the right was greater than the force to the left. Let's take a look at another example. So again, we have 3 charges. They're separated by 40 centimeters. Remember, whenever we have centimeters, we have to convert them into meters, or our force is not going to be in newtons. We are looking at the charge in the middle again. I'm going to look at the forces that are applied to the one in the middle. It is attracted to 3, but it is more so attracted to 7 because 7 is stronger. Then, to figure out our net force, 899 times 10 to the 9th gives me kc. Then in both cases, I will be multiplying by 9 nanocoulombs. So 9, 10 to the negative 9th. Look at that. We can cancel. Yay. Boom. The two charges. And technically, because they're both 0.2 meters away from the middle charge, it's going to be over 0.2, if you will, squared, or you can go straight to 0.04. And then inside I have 7 minus 3 times 10 to the negative 9, because both of them are nanocoulombs. That is 0.04. So that's a 4 over 0.04. That's 100. What I end up with is 8.99 times 9. This is practically a 9. That's another 9. So it's almost an 81 times, I got 100 and 10 to the negative 9. That's 10 to the negative 7th. So I can do 8.1 times 10 to the negative 6th newtons, and the direction will be to the left, and that right here is our answer to this question, where we're looking for the force on the negative 9 coulombs right in the middle between two other charges. There you go.